Good morning, boys and girls, and here's a quickie on linear approximation, aka local linearization. Alright, real fast, easy one for you after some of the more challenging stuff we've been doing. Alright, I got a quick little, again, easy piece of cake question for you here. Piece of cake. Let me bring up my calculator. Now that you can kind of see the screen. My question is just, what is that the graph of? Okay, what equation would you say that is? I know you all got to guess. You can say it out loud. Don't worry. Even if you're, by yourself, headphones on, or, around people, headphones on. What is that? I'm sure you all are thinking, if you did not say it out loud, hey, I know that. That looks like the graph of y equals x, right? Linear function. Well, let's look here. This is again how you, that's not what I wanted. Quick, get out of there. I just wanted to zoom. Go up a little bit more. Zoom out a little bit. Still y equals x-ish, right? Zoom out some more. Wait, that's not looking so straight. What the heck's going on here? That is definitely not straight. That looks like, you know what? I think that we zoom out one more time. That looks like an exponential growth function. That looks like y equals e to the x. And in fact, it is. It's y equals e to the x minus 1. Now, the whole point behind that little fun game and exercise was that if you zoom in close enough to any function, even though that this is a nice curvy function, here at the origin, when we zoomed in close enough, it looked like a straight line, right? Locally, it was linear, okay? And we used that fact quite a bit, especially back in the day before we had calculators, to evaluate things. We used the idea that functions at a very close level are linear in nature. So we can use the tangent line to approximate the function, hence linear approximation. Okay, so these are the two names for this topic: local linearization, because when you zoom in really, really close, it looks like a straight line, or linear approximation, because we can use that tangent line at a point to approximate values that are very near the tangent line, since it is linear right close to the point of tangency. Okay. I guess one other name you might hear this called is tangent line approximation. So linear approximation, tangent line approximation, or local linearization. These three things all mean the same thing. All right, let's switch over to our example now. Okay, we're just going to do one quick example here. F of x equals x plus cosine x. All right, so we're going to say back in the day before we had calculators, we wanted to evaluate, f of 0.1 on this function. But I don't have a calculator. I can't just go plug in 0.1 plus cosine of 0.1 and have it spit out an answer. There were a bunch of tables you had to do. It kind of got ugly. I don't know. It wasn't a lot of fun. So what they came up with instead was, hey, instead of plugging into this function, which is not very easy, let's look at the tangent line close to where we're at. So if I want to do it say at 0.1 or 0.01, let me look at the tangent line that's at 0, 1, since 0 is close to 0.1 or 0.01. And then let me plug into the tangent line. And that should give me an answer that's fairly close to the real thing. And so that's kind of what we're going to do here, is we're going to write the tangent line of this function at 0, 1. And then we're going to use it to approximate some values and see how close they are to the real function. All right? Here we go. If I'm going to write the equation of the tangent line, we need a slope, right? And a point. Well, we already got the point, so I just need the slope. And for the slope, I need to find my derivative. So f prime of x equals 1 minus sine x. And then I need the derivative at 0, so f prime of 0. See, there's all stuff I can do without a calculator. Sine of 0 is 0, so I just get 1. So the slope is 1. The point is 0, 1. So the equation of the tangent line would be y minus 1 equals 1 times x minus 0, or y minus 1 equals x, or y equals x plus 1. That is my tangent line at 0. Now you can see, if this is your tangent line at y equals x plus 1, plugging these numbers into x plus 1 is going to be way easier than plugging into the actual function. You know, negative 0.1, I got my little table down here. Negative 0.1 plugged in here is going to give me 0.9. And negative 0.01 plugged in would give me 0.99. And 0 plugged in gives me 1 and 0.01. I mean, you can see I'm doing this relatively quickly and easily. I don't know if that's behind my picture for you guys, so I'm just going to draw an arrow here. You know, this would be 1.1. I can do that all real fast and easy without a calculator. That took me hardly no time at all. And now let's go and look. We're actually going to bring the calculator back up, and we're going to evaluate these. And let's see how close our approximations were to the real function. Again, because it's locally linear, they should be fairly close. Okay, so I've plugged in x plus cosine x into the calculator here. I've set up our table so that it's on the independent ask, so that I can plug in what I want. And then I plugged in negative 0.1, negative 0.01, 0.01, and 0.1. And now if we go look at our results here, I get to see that, hey, when I plug in negative 0.1, I get 0.895. And now, hey, that's pretty darn close to the 0.9 we got with our tangent line approximation. That's off by 5 thousandths. That's not too shabby for a tangent line approximation. If I go down one on the calculator, whoops, sorry, if I go down, you know, at negative 0.01, we get 0.9899. And now that's even closer to my approximation that we had with the tangent line. At 0, it's right on, because at 0, that is the, you know, point of tangency. Both equations are the same. And then at 0.01, we're at, and again, we want to look down here, not at the number on the screen, because the one down here is the actual number, so 1.00, you know, 99. And again, that's pretty darn close. And then the very last one is, uh-oh, too far, 1.095. I mean, so you can see our tangent line approximation that we used was pretty darn good to the real values, 100 times easier to get. And again, back in the day, you know, before calculators, you could be as accurate as you needed to be, okay? We couldn't, you know, measure out with a ruler any closer than that. So that is a quick little lesson on local linearization or tangent line approximation. You'll have a worksheet that you need to fill out like another, I don't know, about 5 problems. Do something similar to what we did. Write the equation of the tangent line at the given point. Find the values in the table. Compare those with the real values of the function and see how close they really are. It's kind of a fun game. All right. Thanks, boys and girls. See you later and have a nice day.